Okay, so now I'd like to cover the topic of superoperators and the representation of spin operators in something called Leoville space. Now, superoperators are objects which convert one operator into another operator. So let me introduce that as follows. So operators convert one ket into another ket. So we've seen some examples of that now already. So in a single spin half system, when we apply the shift up operator to ket beta, we get ket alpha. So the ket beta is converted by the shift up operator into ket alpha. Superoperators convert one operator into another operator. So this is how you might write that. So this would be a superoperator. And here I'm notating superoperator by using a hat. Acts on an operator and generates another operator. Let's think of some examples. An example which is very common in NMR is a rotation superoperator. In fact, when we talk about NMR, we often use such a superoperator, but without actually using that language. But nevertheless, it's quite intuitive to us, I think. So a rotation superoperator, in this case, would be the superoperator for a rotation by pi over 2 around the x-axis. And this could be applied to angular momentum along the z-axis, and rotates the angular momentum along the z-axis, in this case, to the minus y-axis. So in fact, in NMR, we often use language such as saying that we convert Iz into Iy or something like that. The thing which does the converting is a superoperator. So mathematically, we could say we apply a rotation superoperator and rotate the angular momentum from z to y, or minus y in this case. And in fact, when we apply pulse sequences, sequence of events in NMR, mathematically, we can express that simply as a sequence of superoperators. So a rotation superoperator rotates the angular momentum around a particular axis. Another type of superoperator which is commonly encountered is a commutation superoperator. So if I write Ix but put a hat on top, then what I mean by that is the commutation superoperator of the operator Ix, which when applied to another operator generates the commutator. And the commutator is just the product of the operators combined with order reversed. So this is a more abstract operator, superoperator, but it simply has the action that when we apply this superoperator to an operator, it generates another operator, in this case this one here. And there are many other superoperators important in NMR theory, some of which we'll encounter in a minute. At this point, I'll just point out there's a link between the rotation superoperator and a commutation superoperator. It's not at all obvious. But it turns out that the rotation superoperator, for a rotation through an angle, beta, around a particular axis, in this case the x-axis, is given by the complex exponential of the commutation superoperator. So rotation superoperators are complex exponentials of commutation superoperators. And SpinDynamica uses those properties to calculate properties of superoperators. So let's have a look at how this works in SpinDynamica. So we can start by, let's just set up a spin system of single spin half. We can ask we can use the SpinDynamica contains an object commutation superoperator, which is has this property of generating a commutator. So for example, the commutation superoperator of Ix may be applied to another operator, in this case Iy, and the result of doing that is the commutator Ix Iy minus Iy Ix. Similarly, we have rotation superoperator. Let's have a look at that. So here I set up a 2-spin-a-half system. And I can form the rotation superoperator for a 90-degree rotation about the x-axis for spin number 1. And I can apply that superoperator to another operator, Iy. And I get a result here, which so far doesn't have an obvious interpretation yet. It's the product of 3 operators, 2 rotation operators and 1 angular momentum operator. There's a routine available in SpinDynamica for expressing a particular operator in a convenient way. This expresses the result of the last calculation, but using Cartesian product operators. And we see that the result here is Iz. So here, in this example here, I have my usual axis system. I label with the angular momentum operators. The rotation I'm interested in is about through pi over 2 about the x-axis, and I'm operating on Iy, which now gets rotated up to make Iz. So mathematically we write it as follows, that Rx pi over 2 superoperator acting on Iy gives Iz. And again, to emphasize, this is the sort of thing we do all the time when understanding and talking about NMR experiments, we use the language of superoperators all the time. In the sense we say one operator gets converted into another operator. We can form more general superoperators. So this would be do the rotation through a general angle beta around the x-axis. Again, applied to IY. And the result will be familiar to most of us who do some NMR theory. Let's just have a look at the interpretation of that. So we have Ix, Iy, Iz. What did I do here? I had rotation by beta around the x-axis, so a general angle. Applied to an operator along the y-axis. And the end result is an angular momentum operator in the YZ plane, but at an angle beta from the y-axis. So mathematically, we would have our x beta acting on Iy generates Iy cos beta plus Iz sine beta. And that's what you see that SpinDynamica has generated here. Now, those of us who go into NMR theory at some point get exposed to Cartesian product operators, in which one has evolution not caused by single angular momentum operators, but products of angular momentum operators. Construct an example of that kind. So here, for example, here there's one constructed here. We have a product operator. Let's just write that out first. So we have a product operator 2i1y i2z, and now we rotate that by beta around the x-axis. And here we get a trigonometric expression for that. Which those of us who do the theory of weakly coupled spin systems in solution NMR with product operators will probably be reasonably familiar with. We get a set of different product operators with different trigonometric factors in. Right, so that's rotation superoperator. As I said before, rotation superoperators are given in the technical mathematics, which I'm not going to go into, but the rotation superoperator about a general axis, denoted here mu, is given by the exponential of minus I times the rotation angle times the commutation superoperator of angular momentum along that axis. So we have rotation superoperator and commutation superoperator. Let's generalize that a little bit. So, just to repeat that, so for example, Rx the rotation superoperator is related to the commutation superoperator under Ix. And that generates a rotation around the x-axis. Well, in the product operator theory of solution NMR, we often have evolution not only under Ix, Iy, or Z, but under product operators. So how do we express that mathematically? So for example, suppose we have a spin-spin coupling between two spins, and we make a weak coupling approximation. Now we have evolution under a J coupling between two spins. That would be expressed by an operator 2i1z, i2z. We form the commutation superoperator of that. That would be the superoperator for evolution under a spin-spin coupling. And the theory of that is very well developed. Many of us have played with diagrams of this kind, where you have I1x along the x-axis, you have 2i1z, i2z along the z-axis, and then the third axis here, we recognize that we have ix and we have i1z, so we should have an i1y, and that the I2Z then appears along this axis. These are product operator evolution rules which were worked out many decades ago. So this operator here is generating evolution under this ZZ operator. So we can think of that superoperator as being generating that rotation. So we would expect, for example, that if I start with a density operator component I1x, and apply this superoperator here, that I should get I1x cosine beta, because this thing will get rotated in this direction and eventually makes an angle beta here, and 2i1y i2z sine beta. So that's what we expect would happen. So let's see if SpinDynamica knows how to do that. So I make sure I have a two-spin system. I set up the exponential of minus I beta times the commutation superoperator of this product operator. And apply that to I1x. And I get some complicated formula, so I'm going to try and express that in a form using Cartesian operators. And I get a trigonometric formula. It contains some complex exponentials. So let's ask Mathematica to convert the exponentials to trig formulae. And let's simplify that. And after a little bit of trouble, Mathematica does generate the expected result, I1x cosine beta plus 2I1y I2z sine beta. So again, this was a more complicated example involving the commutation superoperator of a more complex operator, in this case a product of two angular momentum operators. But the result of the calculation has a simple geometric representation. And this type of picture is well used, of course, by liquid state NMR spectroscopists in figuring out how pulse sequences work. But it's all embedded in the mathematics of superoperators and commutation superoperators. So we've looked here now then at commutation superoperators and rotation superoperators. In the theory of relaxation, we go to another superoperator called double commutation superoperator. And it turns out that, as I think we'll cover later in the course, that relaxation in NMR is described in NMR theory by superoperators, and the type of superoperator which are involved in that are actually double commutation superoperators. And actually this is not very complicated. Double commutation superoperator is just the product of two commutation superoperators. So let's take an example. The double commutation superoperator of, for example, Ix and Iy, when applied to a third operator, Iz, just generates the result of applying two commutation superoperators. So Iy commutation superoperator applying to Iz just generates Iy Iz minus Iz Iy. And then we have another commutator. This would now be Ix Iy Iz minus Ix Iz Iy minus Iy Iz Ix plus Iz Iy Ix. So long, complicated expressions, but in the end all they are is just that this double commutation superoperator, when applied to an operator, generates another operator. It's a superoperator. And double commutation superoperators would not be of much interest if it wasn't for the fact that they describe relaxation processes in NMR. So we'll look at them in more detail later, but let's again just go make sure we have a single spin-a-half system. So here again, we've taken the double commutation superoperator, Ix in this case, applied it to Iy, and we get a long combination of angular momentum operators, which we can express if we want in terms of a single operator, and in this case the whole thing reduces to Iy. And we'll get back to double commutation superoperators when we start to look at how to describe relaxation. Another superoperator to cover is a more intuitive one, I think, which is the coherence order filtration superoperator. And that's a piece of cake, basically. All that does is takes an operator and filters out the part of the operator which corresponds to a particular coherence order, and then returns it. It's probably easier to see by example. Suppose we have just a single spin half. And suppose we're interested in, so this construction here would filter out the +1 quantum part of an operator, in this case Ix. And the answer is I1 plus divided by 2. Why is that? So Ix can be written as a half I plus I minus. So Ix contains a +1 quantum part and a -1 quantum part. If we're only interested in the +1 quantum part, we have to just select this component of it. And in this case, it's rather easy to do that. But suppose, for example, that we have a 5-spin-a-half system. And we're interested in the +3 quantum part of an operator I1x, I2y, I3z, I4x, or something like that. Actually, what SpinDynamica is doing now is it has to set up some mathematics for the Leoville space of this 5-spin system. It's finished its calculation, and here it's picked out the 3 quantum part of that operator, some complicated product operator. It contains in there some I1 plus, I2 plus, I3z, I4 plus, multiplied by a complex factor of -1/8 I. Coherence order filtration superoperator will also work if you ask it to filter out more than one coherence order. So those are superoperators. Now, if you remember, I represented operators as matrices. So, for example, I discussed the Zeeman basis of, for example, 2 spins a half. And if you recall, the defining feature of a valid basis is orthonormality, which means that the bracket between any two of these states is 1 if the states are the same, and 0 if they're different. And then we could represent an operator, for example Ix, as a matrix in this basis, with columns given by the basis kets and bras given by the basis bras. Okay. So that's what's called technically Hilbert space. Now it turns out you can do the same thing, but for, instead of kets, you have operators. And instead of operators, you have superoperators. This is called Leoville space. And instead of a basis of kets, one has a basis of operators. An operator basis. Let's call them Q1, Q2. And a valid operator basis for Leoville space has the property of orthonormality, just the same. The bracket for operator we write with round brackets rather than angled brackets. So the bracket between any two basis operators is 1 if they're the same operator, and 0 if they're different operators. But what's the bracket between two different operators? This is mathematicians have figured out how to do this. And this construction here, which is called Leoville Bracket, relies on the matrix representations of these operators in Hilbert space. What happens is you take the matrix representation of one operator, you do an adjoint thing on it, you multiply it by the matrix representation of the other operator, and then you take the trace. So what's all that about? The adjoint, this dagger, is no big deal. It just means you take the transpose of the matrix and you also take the complex conjugate. So it's just some funny manipulation of the matrix. Exchanging rows and columns, that's what transpose means. And changing the sign of all imaginary numbers. That's what complex conjugate means. And trace means sum all diagonal elements. So this is very technical mathematics. We don't really need to worry about it because SpinDynamica just handles that for us. But the point here is that you can then represent a superoperator as a matrix in Leoville space, just like you can represent an operator as a matrix in Hilbert space. So let's see some examples. So just to repeat then, so an operator basis for Leoville space is a set of operators which are orthonormal, which means they're orthogonal and also normalized, which is defined by this Leoville bracket thing. And SpinDynamica contains a Leoville bracket routine. So for example, if we set the spin system to a single spin half again, we can take the Leoville bracket between Ix and Iy. And the Leoville bracket between two operators, Ix and Iy, is 0, which means those operators are orthogonal. Which is not a surprise, they're represented by angular momenta along orthogonal axes. and that bracket, the Leoville bracket between Ix and Iy, is 0. We can break that down into its components. If we take the matrix representation of Ix, it looks as follows there. If we take the matrix representation of Iy, it looks like that. If we take the matrix representation, if we take the product of those two matrix representations, we get that, and you can see that the diagonal elements are opposite in sign. So the trace is 0. So that was one of the properties of Leoville space, is that the operators which form Leoville space should be orthogonal to each other. So the Leoville bracket is 0 for different operators. Another property, though, is that the Leoville bracket between the same operator should be 1. That means an operator should be normalized. Now that's normally usually not the case without a bit of intervention. So if you take the Leoville bracket between Ix and itself, then the answer is a half, it's not 1. Which one can also see if one multiplies out the matrix representations. Matrix representation of Ix multiplied by itself is this matrix, and you can see the trace is not 1, it's a half. So to get the right operators for Leoville space, they should be orthogonal, but they should also be normalized. So SpinDynamica also provides routines for determining the norm of an operator and for normalizing an operator to make sure that its norm is 1. So for example, the normalized version of Ix is in fact root 2 times Ix. So there's a little bit of technicalities there, that the operators used for Leoville space should be normalized, so they often have these extra factors in them. So let's look at some bases. Suppose we have 3 spins a half. The default operator basis, which SpinDynamica uses if you don't tell it to use something else, is called the shift and Z operator basis, which has been sorted according to its coherence order. So let's just have a look and see what that is. So the operators which form that operator basis look like this. You can see a whole bunch of product operators with I minus operators. The first one is I1 minus, I2 minus, I3 minus. And then there's a whole bunch of other operators coming in here with some Z operators appearing. I1Z, I2 minus, and so on. But the nice thing is that those operators have been set up for you, so they're already orthogonal and already normalized. And furthermore, they've been sorted, so they're in a nice arrangement with respect to coherence order. So if we take the coherence order routine, this is mathematical language for mapping a function onto a list. This says for all of those basis operators, for each of them, apply coherence order. Technically, that maps this function onto each of the operators and generates a list of the coherence orders. And here you can see that the -3 quantum operator is first, and then there's a whole bunch of -2 quantum operators. Then more -1 quantum, and then 0, and so on. How many operators are there? That's given by the routine operator basis dimension, which tells you that there are 64 operators in this Leoville space. So again, SpinDynamica forms the Leoville space by default here, the shift and Z operator basis. But SpinDynamica actually allows you to use many different forms of operator bases, including ones you can define yourself. But another very common one is the basis of Cartesian product operators. So again, we have a 3-spin system. This time we ask for the Cartesian product operator bases. And this time by default, there are different options, but by default it's been sorted not by coherence order but by the spin product rank, which means, which is maybe easiest to see by example, these are the basis operators for the Cartesian product operator bases. The first one is just the unity operator, normalized by some factors here. And then we have a whole bunch of Ix, Iy, Iz operators for the 3 different spins. So these are single spin operators. And then we have a whole bunch of 2-spin operators, and then a whole bunch of 3-spin operators, and so on. So this is what's meant by spin product rank. Spin product rank of a 1-spin operator is 1, a 2-spin operator is 2, and so on. So SpinDynamica then has set up a nice Cartesian product operator basis in which to, again in this case, 64 of them for the 3-spin system. So having set up a set of suitable bases, or allowed SpinDynamica to do that work for you, one can then represent a superoperator by a matrix. Just like an operator was represented by a matrix in Hilbert space, a superoperator is represented by a matrix in Leoville space. And how does that matrix representation work? In Leoville space we have the kets, which are the sets of basis operators. We have the bras, and we have a matrix for the superoperator where a particular element in the matrix representation is given by the Leoville bracket of the superoperator by the 2 operators. Now I have to say that these things, the superoperator matrix representations, can be pretty tricky to work out by hand and extremely laborious. So people involved, for example, in relaxation calculations previously had to spend a lot of time and paper in figuring this out. And it really is a substantial piece of work, and this is really where SpinDynamica is extremely useful for people in those fields. So here's an example. Set spin system 1. Let's set up a single spin a half again. Let's set up the Cartesian product operator basis. For a single spin a half, this is pretty trivial, but let's look at it. It's a set of 4 operators. The X, Y, Z operators, which have these normalization factors in them, and also the unity operator, also normalized. So the matrix representation of a superoperator is going to be a 4 by 4 matrix. So this will be a rotation superoperator by beta around the x-axis. And here SpinDynamica has been asked to evaluate it and then simplify it. And we see a 4x4 matrix, and we see that it has some trigonometric factors, cosine beta, sine beta. In fact, one can recognize actually that this 3x3 part of the matrix here is just a rotation matrix, which you would use in classical mechanics for the rotation of an object around the x-axis. So SpinDynamica here has essentially shown that the matrix representation of a rotation superoperator in this particular basis maps onto classical mechanics, which is what we all know in NMR. That's why we use three-dimensional axis systems and why we can use our hands and three-dimensional visualization capabilities of our brain to figure out how pulse sequences work. If we rotate around the y-axis, then again we get this 3x3 matrix here would be the 3x3 matrix involved in the three-dimensional rotation about the y-axis. When we go to higher spin systems, things get a little bit more tricky. So if we have a 2-spin-half system, and again set up a basis of product operators. So again we have the unity operator, we have a bunch of 1-spin operators, and then a bunch of 2-spin operators. And again we can ask, what is the rotation superoperator? What's the matrix representation of that? And now we get a larger matrix, 16 by 16. But you can see it contains all of these little subspaces which represent the rotations of operators with respect to each other in that space. Now, before finishing this lecture, I just want to show an example of a more complicated superoperator. And here I skip ahead, but it's maybe good just to show you what this looks like. This is a relaxation superoperator. Something we would use in spin-dynamical calculations for figuring out what happens when you have dipole-dipole relaxation, as involved in the nuclear Overhauser effect, for example. So here again we have a 2-spin-half system. Here I've just set up again the shift and Z operator basis chosen here. So the basis operators involve products of shift operators, I1 minus, I2 minus, and Z operators arranged according to coherence order, which we can examine by evaluating the coherence orders of all the basis operators. And we see a single -2 quantum operator, and then we have 4 -1 quantums, 6 0 quantums, 4 1 quantums, and a 2 quantum. And now I write down the relaxation superoperator, gamma. Now this theory is going to be covered later on this week. But in this case, this is actually the relaxation superoperator for a molecule containing 2 spins a half, which is randomly tumbling in a liquid. The coupling between the 2 spins is described by a dipole-dipole coupling constant, which is given here as symbol B. We can look at that in more detail later. It involves the inverse cube of the distance between the 2 spins. Correlation time, tau c, that describes how rapid the molecule is tumbling. And this particular form of the superoperator actually here assumes a particular approximation, which is called the extreme narrowing limit, which means that the molecule is tumbling more rapidly than the spin precession, the Larmor frequency of the spin. So this would be appropriate for a small molecule in a liquid. It would not be appropriate for a macromolecule, where we have a slightly different form of the relaxation superoperator. But if a small molecule in the liquid, this would be a good approximation for the superoperator. And it's a double commutation superoperator. Actually not just one, but it's actually 5 double commutation superoperators, which involve the double commutation of 2 different operators, and those are spherical tensor operators, which are these opt things which I talked about briefly before. So we'd have the double commutation of 2 spherical tensor operators of rank 2. Well, it's a complicated theoretical construction. It involves quite a few complicated concepts here: spherical tensor operators, double commutation superoperators, and so on. But you can see it's a pretty concise expression. It's summed over 5 operators, actually. That's where this sum here comes from, because the spherical tensor operators have 5 components. So it's the sum of 5 double commutation superoperators, some of which refer to these complicated spherical tensor operators. Doesn't matter. SpinDynamica can evaluate the matrix representation. This would be a graphical representation of it. And actually you see these blocks. These blocks actually have an important consequence. In the old days, maybe it's not sure it's fair to say that, but in the old days, part of this would be called a Redfield kite, because this block structure, if you're not too worried by aesthetics, you could ignore half of this and then think of this as a kite with a sort of tail hanging off. It's not a very good kite, in fact, but that's what people call it. And the structure of that has a lot of important consequences. It has a great deal of zeros here. And those zeros tell you something physical about what the relaxation can or cannot do. In fact, the relaxation does not convert one type of coherence into another type of coherence. In fact, there are more zeros here. Those are interesting zeros. There's a long-lived state in there, something we can look at later. And we could, if we want to, go in detail, and we see the actual form of these superoperator matrix elements, and you see all these dependencies on correlation times with strange factors. In the old days, people would spend days and sheets of paper in deriving this stuff and make a lot of mistakes. And I think maybe we'll see manually exactly how some of these elements arise later. So the basis operators here, remember, have been ordered according to coherence order, so this kite structure comes out nicely. And here I've just programmed in a Mathematica construction just in order to label this a little bit more neatly by meshing out this block structure and labeling it with the coherence orders. So what you see is that there are blocks here. There's a single operator here, which is the 2 quantum operator, and that is not converted into anything else by this type of relaxation. There are 4 operators which are single quantum operators, and you can see that the single quantum operators are not converted into any operators which are not single quantum. So the only conversion which takes place is within the single quantum subspace, and actually there are 2 different subspaces in there which don't mix with each other. That's not completely obvious, and that has some consequences for particular experiments. That sort of mixing there would actually be explored in the Rosie experiment. And then you have the 0 quantum block, which actually contains 6 operators. One of them is the unity operator, which comes in down here actually and doesn't mix with the others. And then again you have 2 0 quantum blocks of operators which don't mix with each other and don't mix with any of the others as well. And in that block there, actually in this block here, there's a little 2 by 2 block here. In that block is the Nosy experiment. all of nosy is contained in that little block. Here there would be some cross-relaxation between operators, between two spin operators in here. And then the whole thing is pretty much mirror imaged in the -1 quantum and the -2 quantum block. So this is where the mathematics of operators and superoperators connects with the spin dynamics. By going into these, forming these superoperators, looking at the relaxation properties, one can derive not only qualitatively what's going on, which operators mix with which other operators, but also, if you want, quantitatively. So one could build superoperators in SpinDynamica. Here, this single line of code here gives you the relaxation superoperator for two spins relaxing with each other, cross-relaxing with each other with a dipole-dipole relaxation in a particular motional limit. But you can make this as complicated as you want, building in any different assumptions about the relaxation, different motional models, in a completely arbitrary way, and rapidly get analytical results for how the relaxation works. So with that, I conclude this lecture. Thank you.